is what, 1.4. Inequalities. And set notation. So let's start with just solving inequalities. So the solutions to an inequality, a solution is any value for an unknown. In this case, when we solve equations and inequalities, our unknown is represented by a variable, right? That makes the statement true. Whoops. That makes the statement true. So, for example, let's do like x is greater than 4. Is there one solution to this? There's like infinitely many solutions, right? Because every single number that's greater than 4 is going to make that statement true when I replace x with it. Is 4 a solution? No. It's not, right? Because 4 is not greater than 4. We call this a strict inequality. Strict inequalities do not include their endpoints. So in this case, when we say n, it's got an n in it. When we say endpoint, we sort of literally mean like if you were to graph it on the number line, like the point that separates the solutions from the non-solutions is what we call the endpoint of that set. And in this case, it's 4. A strict inequality tells us that 4 is not included in the solutions, right? So since that endpoint is between the solutions and the non-solutions, we have to specify if it's part of the solution set or part of the non-solution set. And the way we do that in terms of the inequality is based on which symbol we use, right? So this is an inclusive inequality. Which, as the name implies, it does include the endpoint. So the solutions to that inequality are any numbers that are either greater than 4 or equal to 4, right? So again, on the number line, let's just go ahead and graph it. So if I have a number line, and I'm not going to be like super formal about the number line. I'm going to mark only the number I really care about instead of like marking the whole thing off because we don't really care. There's a couple of ways to express these on number lines, and probably the one that you've seen most often is like an open circle or like a closed circle, right? So if we're including that 4, we use an a closed circle. When we're not including that 4, we use an open circle. I'm going to change this notation slightly because it's different in our book, and also the other notation lends itself really nicely to interval notation, which is what we're about to talk about and what we'll use for most sets. So instead of using a closed point to represent inclusive inequalities, we'll use what we call a hard bracket. So we call this a hard bracket. Which represents a closed set or a closed point. And then, dang it, I messed up. I can't undo that point. after I write all that other stuff. Okay. So this is a hard bracket. And I have it pointing to the right because the solutions to this set are all the numbers that are to the right of 4. And so to finish graphing that set, I would shade everything to the right of 4. And then for the other one, we're going to use what we call a soft bracket, which is, it just is like a parenthesis. And again, I'm going to shade everything to the right of 4 to show that all the points to the right of 4 are solutions to my set. So if you used open or closed points, like to graph these, like I wouldn't really care. In my math lab, you'll see the brackets. And when we start talking about interval notation here in a sec, you'll see the relationship, like how we use the brackets in interval notation. So I kind of like using the brackets on graphs as well, because then we can go straight from the graph to the interval notation. So let's talk, what else do we want to talk about? Oh yeah, so we'll just do this. So ways to express. Sets of numbers. I should be more specific. Infinite sets of numbers. So we have other ways to express finite sets, which are like sets that have, like you can list what's in there. Like the set 1, 2, 3 is a finite set because it contains like 3 numbers. Whereas the set of all numbers greater than 4 is an infinite set because there's an infinite number of values that are greater than 4, right? So we're just talking about sets right now that we can express with inequalities, which always contain an infinite number of values. So let's start with an inequality, which is kind of something we've all seen before. Let's say x is less than or equal to, or let's even do this. Let's say that x is between 3 and 9. So anytime you have what we call a compound inequality, where the variable shows up once and then there's an inequality on either side of it, the inequality symbols always have to be pointing the same direction. And so this is really 2 inequalities. It says that x is greater than 3, and then it also says that x is less than or equal to 9. But when that variable's in the middle, like it literally means like x is between 3 and 9, just like it looks like. So then we can graph this. On the number line. So I'm just going to mark 3 and 9. Am I including 3 in my solution set or not including 3? We're not including 3, and so we'll use a soft bracket at 3. And then we are including 9 because of that or equals to sign. And we'll use a hard bracket there. And then everything between 3 and 9 is a solution, so we'll shade everything between 3 and 9. So then when we use interval notation, in general, interval notation will either have a soft bracket or a hard bracket, and then it'll have the smallest number in the set, a comma, and then the largest number in the set. And then another either soft or hard bracket. So in this case, the smallest number in the set is what? 3. And on to the left of 3, I'm going to use a soft bracket because I'm not including 3. And then the largest number in the set is 9. And I do want to include 9, so I'll use a hard bracket there. So can you kind of see how you can go from like the graph to interval notation? Like they look really similar, right? So we're starting at 3, not including it, going up to 9, including it. So graphing, if you're ever unsure about how to write an inequality in interval notation, graphing it can be really helpful because you can kind of translate straight from the graph to that interval notation. Any questions so far? So these look a lot like ordered pairs, especially if you have soft brackets on both sides. So what it really comes down to is context. You kind of just have to use the context of the problem to like figure out if that's an ordered pair or if it's an interval. And we will talk more about that as we start working with things in 2 variables. But for now, we just want to note that like what that say, it's not 2 numbers. It's not like the number 3 and the number 9. It's saying that our set is everything from 3 through 9. So our x value can be anything from 3 to 9. And notice it's not like parentheses in the sense that we use them in expressions, like they don't have to match. So the parentheses or brackets just tell us if we include the endpoint they're close to, right? So that soft bracket tells us we're not including the 3, and then this hard bracket tells us we are including the 9. Oh, wait, there's one more. Set builder notation. So set builder notation, to be totally honest, is somewhat useless in this setting. Like it's a little bit silly to use in the setting that we're using it, but we want to introduce it because it does come up later and is very useful later. It works a little better, or it makes a little more sense when there's more than one restriction on what your variable can be. So when we do inequalities, like there's like one restriction, right? If we say that x is greater than 4, that's like one condition that our variable has to satisfy. If you have like a bunch of different conditions your variable has to satisfy, then like set builder notation makes a little bit more sense, but we're just going to use it so we can get used to the notation itself and like what all the symbols mean. So set builder notation is a curly bracket. Sets in general, anytime you see curly brackets, other than if they're just being used in the place of parentheses, like they always represent sets. And then we write x, and that's just telling us like what variable we're using to represent a member of the set. So we're just saying x is the variable we're going to use to represent whatever is a solution to this. And then we do a line, which is read such that and then we list the conditions that the members of our set have to satisfy. So in this case, and this is kind of why it feels a little silly, is like you're just copying the inequality. But in general, like what comes after that line are just the conditions that members of set must satisfy. So we read that x such that x is between 3 and 9, essentially. Again, we'll see it a lot, and I think it might come up on your homework a little bit. There might be like some like solution sets that are in that form, but we're going to use interval notation more often. Yes?
So we don't have to do, so we did this last year, you don't have to do the x is the element of all real.
No. Okay, great question. So in general, we usually say like what set X is a part of. So the biggest set of numbers is the complex numbers. It includes all the real numbers and all the complex numbers. In general, we usually say X is a real number or X is a rational number or what have you at that beginning part. So it tells us the general set that it's part of and then those restrictions. In this class, we are working strictly with real valued functions. And so every single number we talk about, we will assume is a real number. And so that's why you don't have to write that. If you write it, that's fine. You won't see it like in the book or in the homework or anything, just because this class is strictly restricted to real valued functions. Okay, let's solve some inequalities. So solving inequalities. We will use the same exact process as we did to solve equations. With two exceptions. So the first exception is maybe somewhat obvious, which is that you're going to use an inequality symbol. In every step. Instead of an equal sign. So inequalities start with an inequality symbol between the two sides. You want to maintain the inequality symbol between the two sides in every single step. So sometimes I see people change that to an equal sign, solve it, and then try to replace it again, which can get a little bit troublesome if things switch sides or if we change the direction of the inequality symbol. So it's best just to carry it with you throughout the entire problem and not kind of try to guess which way it goes at the end. Probably 80% of the time you would guess right, but for that other 20% of the time, it would kind of stink. And then the other exception is that at any point, so if at any point you multiply or divide both sides by a negative number, it reverses the direction of the inequality. And that mainly has to do with the fact that multiplying and dividing by a negative changes the sign on the numbers, right? So if I have a number line, let's put 0 right here, and we'll say 2 is here, 5 is here, -2 is here, and -5 is here. Well, we know that on the number line, bigger numbers are to the right, and smaller numbers are to the left. So if a number is to the left of another number, it's less than. If a number is to the right of another number, it's greater than. So if we look at 2 and 5 on the right side, I mean, we all kind of know that 2 is less than 5, yeah? Mm-hmm. if I multiply both sides of that inequality by -1, that gives me -1 times 2 is theoretically less than, I'm just not going to write a symbol. And then -1 times 5, which gives me -2 and -5. Well, what's the relationship between -2 and -5? -2 is bigger, right, because it's further to the right. So that switches. And it's because what we're doing is we're essentially taking these 2 points and like flipping them over 0 on the number line. So it's sort of like a mirror. So what used to be further right is now further left. And so what used to be greater is now less. Right, so that is bigger. And that is less. Yes?
Is that the same with dividing by negatives?
Yes. Yeah, because dividing by a negative changes the sign on the numbers as well. So it does that same like reverse thing. So we want to think of like 0 kind of as like a mirror, and we like flop over it. So the entire inequality flips. Another thing that I guess sometimes comes up is if you're solving like 2 or 10 equals 2x, like some of us get in the habit of being like, oh, x equals 5, which is like true, and it works just fine with equations to just kind of like flip the sides, be like, oh, I like my x to be on the left, right? When in reality, like what we did was we divided both sides by 2, and that would give us x on the right and 5 on the left. But with equations, like it's totally fine to just be like, oh, that means x equals 5. The same isn't true with inequalities. Like if I have 10 is less than 2x, we can't just be like, oh, I like my x to be on the left and switch sides the same way we can with equations, because the side that it's on makes all the difference in terms of which is bigger and which is smaller. So if you like your inequalities, or I'm sorry, if you like your variables on the left, you can flip the whole thing. So when we divide both sides by 2, we get 5 is less than x. Well, if 5 is less than x, that's the same as saying that x is greater than 5, right? So if you took that entire thing and flipped it over, so you'd have x there, 5 there. Right, so just make sure that if you do change sides, that the pointy side of your inequality is still pointing towards the same number, right? So like the inequality always points towards the smaller thing. So in that second line, the inequality is pointing towards the 5, and when I switch it, the inequality is still pointing towards the 5. So if you're just conscious of that, like which number it's pointing towards, then you can switch all you want as long as you maintain that relationship. Good? Okay, let's solve a couple of these. I like 6 better. -2. Okay, so I'm going to start by getting the variables on one side. There's sort of a couple schools of thought when we solve inequalities. Some people really like everything to stay positive so that they don't have to switch the direction of the inequality, in which case I suppose the first thing you would do is subtract 4x from both sides, right? Because then like you have a positive 2x instead of a negative 2x. I'm in the camp where I just really like my variable on the left, and it's not like a right or a wrong thing. It's just like a preference thing. Like I don't know, I just like my variable to end up on the left side. So what I would probably do is subtract 6x from both sides first, and it doesn't matter which one you choose. Like you get the same answer either way. So it's totally up to you. I'm going to just do it the way I usually do it. So I'm going to subtract 6x from both sides, which gives me a negative 2x minus 1 here, and then a negative 2 there. And then I'll add 1 to both sides, so I have negative 2x is greater than or equal to negative 1. I can do that. And then I'm going to divide both sides by negative 2. So since I'm dividing by a negative, that's going to switch the direction of my inequality symbols. So I get x is less than or equal to positive 1/2. So I'm going to write my solution in interval notation, and I'm also going to graph it. So since we're graphing anyway, we might as well graph first because it kind of helps with the interval notation. Here's a half. Should I use a hard bracket or a soft bracket?
Hard bracket.
Hard bracket, and we're pointing to the left. And everything under 1/2. Another nice thing about getting your variable on the left is if your variable's on the left, the inequality like literally mirrors the arrow that you'll shade when you shade on your graph, right? Like, so if the inequality is pointing left, you're shading to the left. But that's only true if your variable's on the left. And then in interval notation, so we have no smallest element of our set, right? Like, because we don't have any number on the left side that x is greater than. And so that tells us that that our set just goes all the way to negative infinity, we say. So if there's no smallest element, we always use soft brackets at infinity and negative infinity because it's not a number you can actually be equal to. It's just telling us that we are constantly getting smaller, or we get infinitely smaller. So negative infinity. And then the largest element of our set is 1/2, which we are including in our set. So we'll use a hard bracket. Let's do one more of these. So we're going to solve and graph. So 2/3 times 7/8 minus 4x minus 5/8 is less than 3/8. So I see fractions, which makes me think of clearing fractions. But when you also have parentheses, like, you want to kind of think about if it's going to make more sense to clear fractions first or if it's going to make more sense to distribute first. Like on the homework that we did Monday night, there was one where, like, if you distributed the fractions, you ended up not having to clear fractions at all because all of the numbers in the parentheses were divisible by, like, whatever the denominator was. And, like, it wasn't wrong to clear fractions first because, like, you still got the same answer. But if there's both parentheses and fractions, it's sort of worth thinking about, like, does it make more sense for me to distribute first and then clear fractions, or to clear fractions and then distribute? In this case, I would distribute first only because I can't clear that 7/8 by multiplying both sides by anything at this point, right? Like, if I multiply both sides by 24 at this point, that would clear the 3, but then I'm still going to have that 7/8, and I can do some distributing to get rid of it, but I would just probably distribute first and then clear all the fractions at once. So if there hadn't been a fraction in the parentheses, I probably would have cleared fractions first. And there's not a right or a wrong choice as far as which one you do first, just sometimes one is a little more efficient than the other. So let's see, 2/3 times 7/8 is, that 2 cancels, so we get 7/12. Right, because of that. And so then you have 1 times 7 on top and 3 times 4 on the bottom. I don't particularly like that notation, but that's what's happening. And then remember that any whole number is just over 1. So 4x times 2/3 is just 4x times 2 over 3 times 1. So this is going to be 8x over 3. And then minus 5/8 is less than 3/8. So then now I can clear fractions by multiplying both sides by 24. You have two choices when you multiply both sides by 24. You can either, I meant 24, not 12. You can either write 24 and then put the entire left side in parentheses. And then the entire right side, which in this case is just one term. Or you can say, okay, I'm going to multiply 24 over 1 times each term individually, which is really just distributing that 24 from the previous step. But I'm totally fine if you skip this altogether. And the reason I bring this up is that what you can't do, here, let me finish writing it. I'll mess up if I try to write and talk. 24 over 1 times 3/8. So what it is not okay to do is to go 24 times and then times 24. Because that's not like mathematically accurate. Like what that's saying is that you are multiplying 7/12 by 24. And that you're multiplying 3/8 by 24, not that you're multiplying the entire left side by 24. So I'm fine if you only want to write the 24 once, but if that's the case, you need to be really careful that you're doing the entire left side, so in parentheses by 24. So if you don't want to write it out every single time, that's totally fine. Just be careful that you're not like shorthanding it. I don't grade by the like, oh, I know what you meant method. So if it's not mathematically true, then it's not correct, even if I know what you meant. Only because those types of things are the types of things that come back to bite us later on, right? Like when notation becomes more important and the problems become more complex. Those things where we sort of know what we meant, but we weren't actually writing what we meant, come back and like mess us up later. So even if they don't mess us up now. So that's why I pay such close attention to that stuff. It's not because I'm trying to be like a mean hard ass. Okay, let's simplify. So 24 divided by 12 is 2 times 7 is 14. 24 divided by 3 is 8 times 8x is 64x. 24 divided by 8 is 3 times 5 is 15. And then 24 divided by 8 is 3 times 3 is 9. If you're still at all unsure about clearing fractions or how to do it, definitely come see me so we can go over it together. If you didn't do it on that first homework, I asked you to redo the problem just because it's a skill like we're going to need. But I just want to make sure everybody knows how to do it, at least on this first one, just so I can see you do it once. So now let's combine like terms. We have negative 64x minus 1 is less than 9. We'll add 1 to both sides. And we have a negative that we're dividing by, so this is going to be greater than and 10 over negative 64, which gives us x is greater than negative 5 over 32. And when you graph something like this, like say you're given a number line, which like if I asked you to graph on the test, I'd probably give you a number line that's like already marked off. Like so. And like negative 5 30-seconds, like what two numbers is that between?
0 and -1.
Yeah, 0 and -1. Is it closer to 0 or closer to -1? It's going to be closer to 0, and the reason we know is that 5 is closer to 0 than it is to 32, right? So as far as like graphing this, like I'm not asking for exactness, but you know, like you should put a mark somewhere closer to 0 than to negative. So between 0 and -1, but maybe a little closer to 0. So it's probably like right around there is good enough for me. We're going to use a soft bracket because it's a strict inequality and we're pointing to the right. So it is everything greater than -5/32. And I'll just kind of throw that on my graph to show that that's what that mark is. And then in interval notation, my solution, the smallest number in my set is -5/32. I am not including it. And there is no largest number in my set, so we go up to infinity. Again, always use a soft bracket at infinity or negative infinity. And then I'm going to hand back, let's see, your homework for tonight. So for tomorrow, you have 1.4 in my math lab. And then you also have 1.4 written homework, and it's in the text. I want you to write your answers. So write your solutions in interval notation. Whoa, if I can spell. I have one more math problem for you guys. Notation. So it doesn't ask you to do that in the text, but I am asking you to do it. And it's noted on your homework calendar as well that you should write it in interval notation. And then you're going to have corrections on the R.4 1.1 homework that I'm about to hand back. For corrections, remember you're going to redo every highlighted problem. On a separate sheet of paper. Unless, like, if you didn't use the back or something on your homework, you can do it on the back. I just want it to be separate from the original one so you're not, like, tempted to, like, erase a number and just change it. And then staple it to your original assignment. To turn in. And I will say, like, I write on your homework a lot, and sometimes I'll make comments, especially about some, like, notation or, like, a sign or something that, like, I don't think it's necessarily worth you redoing the entire problem for, but I will make comments on problems even that I don't have you redo. So be sure you read it, like, even if it's not highlighted, just take note of whatever feedback I give you on it so that you can adjust going forward. Okay, so while I'm handing back homework, what I want to know is, this is not homework, it's just something we're going to talk about in a second. Is this set, I guess the correct way to say this would be R. R. Not an English major, I try. And this set the same. So I'm going to hand back your homework while you think about that and or mess around with it, and then we'll talk about it before we leave. If your homework has a score at the top, at this point it would be 100% because it would mean you got everything right. You don't have to turn it back in. So as soon as your assignment has a score on the top, you're done with it. Okay, yeah, that's fine. Let me look for it. I didn't see, did you do it like recent, like this morning?
No.
No, okay, let me look for it. It might be in my, my spam, for some reason some people just said it's my spam. Thanks for letting me know. I will look for it. Oh, no, not for me. If you, in your app.
Okay. Steve, thank you.
Or- And oh, thank you. This one? There you go. Okay. I'm getting it. Eventually. Hey. Late. Brandon. Trent. Emma. Logan. Michael. Rachel. I think we have two Jakes. Do we have two Jakes? I don't know where Jake. Here. So if you're not sure on this one, try graphing them both. It makes it somewhat obvious. Jamie. Okay. And then Alex. Bella. And Zach. If you turned it in yesterday, it's possible I didn't get to it. Like I tried to sort through the ones from yesterday that were Monday's homework, but if I missed one, that's probably why you didn't get it back if you handed it in yesterday. Yes.
I did have it
On the day it was due? Okay, let me remind me of your name again.
Josephine.
Let me look through my other ones. It might have just gotten in another pile. But first, let's talk about this real quick. Are these the same?
No,
Why not?
because x greater than 4 includes more values than x greater than or equal to 5.
Right. So if we take this, so the reason that we have these strict inequalities and inclusive inequalities is because we can't just jump from an integer to an integer, right? So x is greater than 4 includes all of the numbers between 4 and 5, whereas x is greater than or equal to 5 doesn't include those numbers. So if 4 is here and 5 is here, these are what the two sets look like. So notice, all of these numbers get left out if we jump up to the 5, right? So that's what that strict inequality allows us to do, is we get infinitely close to 4, but it's not actually equal to 4. So 4.00000000000000001 is in this set, right? But it's not in that set. So that's why we have the two different inequalities, is so we can get infinitely close. So that's just something you want to be careful of as we talk about greater than and greater than or equal to, is that we're not accidentally jumping over all those in-betweens by using an inclusive inequality instead of a strict inequality. And then you guys are all set to go. Josephine, I will find that homework right now.
Thank you.
Thanks, see you tomorrow.
So, you said the homework due today.
Yes.
Just like a question on one of the
Uh-huh.
problems.
Yes.
So you said I can just put them in there and turn it in there?
Absolutely, yes.
Sweet, thank you. There should have been 2 homeworks, right? Or is it just 1?
I just gave back one today. I'm a little behind for this first week. See, the thing is I remember seeing your name. Like, which is disconcerting to me. And I even marked that you turned it in. Maybe I put it in. But that.
So, for this one, did I just forget to do that?
Yeah, like you actually just did. No, what, circle it? No, you just didn't finish. Like there's one more step. Like you have to divide both sides by 3. Right, because you told me what 3x is equal to, just not
Yeah.
what x. Yeah, so that's all it was.
Okay. And then I did this one, but I turned it in yesterday, I think. Or
Okay, yeah,
Tuesday, so-
I know some people like turned it in yesterday, so I'll find it and just add it to it. I just wanted to make sure that you were aware. Oh, I just found it. It's right here. And it's not graded. But I can grade it really quick. Because I can kind of see already, like, this one.
You went to nationals for shield sports at 4-H? Same, bro.
You know, what year?
Oh, there it is.
Concept.
What did you shoot?
And-
Shop.
Okay, cool.
Okay, so I'm just going to tell you instead of writing, so to save some time. This one, I think it looks like you just dropped that negative.
Oh, okay. Makes sense.
Oh. And maybe lost the 2/3. Like when you multiply everything by 3, you get negative 7x
Yeah,
plus
I lost
2.
plus 2/3.
Okay. And then on this one, nine. Oh, same deal. So, oh no, that is a plus. Plus, minus. This should be a 4. Yeah, so 6 divided by 3 is 2. So really, like,
Just
minor
very,
little
very
things.
small.
So I would just, often, like, when I have people do corrections, I tell them to, like, not look at what they did the first time, because, like, mistakes like that, you probably won't make a second time. So if you just, like, write the problem and do it again and then compare, like, often you'll be like, oh, yeah.
Okay.
Right? So just try that, and you probably won't make the same mistake.
I tend to do that a lot, so it just makes it focus a little bit more.
Yeah, I do the same thing. Nice. I always do things like 4 times because I know that I just make like careless mistakes.
Mistakes.
Yeah.
Alright, thank you.
Cool, you bet.
How's your morning?
What? It's great. I'll be right back.
Okay.
So for like from 8 to 12, and then got up at 12 and then left to take a shower for like an hour. Maybe, I don't know. Yeah. You sleep. I moved to, you can or better than like that anyway. There's a picture of
Yeah, so you just buy the book and they email it to you, I think. And then it gives you the instructions. Like, click here.
just randomly look at the
And like, we have a sequence that has like activated
Gas
and stuff.
You're
Yeah. Oh, it gets in there.
Is it attaching or is it just a master?
It'd be awkward to take a bath in the shower right next to it with no curse. You're all just chilling in there, so I'm gonna take a shot and like suck her up.
It's not hot though. To make it hot, it was like 6 minutes. It's just solid, little cup holders on the side.
Yeah. And then to heat it up, you just throw it out in the window.
That was true.
Maybe a microwave.
Just something.
Carpenter. I get them.
Just bring the loader up and throw the leaves in there.
What do you do?
Pulls a lot more electricity, which you would need. How's it going?
Give away the answer. Okay.